Hi guys, good morning. Hope you're all doing well. Right. So we have how many participants? 7 people, I guess. We have only 6. 1, 2, 3, 4, 5, 6. Maybe we wait for
Good
maybe
morning,
1 or 2 minutes. Sorry?
Good morning, sir.
Yeah, good morning. Good morning. Yes, good morning. So we'll just wait for maybe 2, 3 more minutes. Let your friend join. Okay. So guys, in your school, have they started this chapter? Have they completed this chapter? Chemical reactions and equations?
They completed, sir.
They completed the chapter. Okay, very nice. So are you finding it helpful, what we are studying here and what they're doing there? Are you finding it helpful?
Yes, sir.
Okay, fine, nice. Okay, I think now we have enough people. I think we can start. We almost have 10 participants. Right, okay. Let me share my screen and start. Today is 13, right? Okay. Right. So yeah, so last class we saw a lot of stuff, right? So we said we were actually looking into what are the different types of information other than the reactants and products. What other extra information you will be able to give along with the chemical equation. So I told you that one of them, say if you can recall, say one of them was including this upward arrow symbol, right? So can someone tell me what does this mean, upward arrow symbol? Yes, what do you mean by this? What does it represent?
Gas,
The
sir.
upward arrow. Okay, gas. So just a gas or anything else you have to add to that? Reactants, products, anything you want to add?
Sir, it may be both of them, sir. A reactant or product.
No. So
Only in the
it's,
product
remember,
side, sir.
correct. It should be only in the product side. It is evolution of gas. That's what it means. Obviously, evolution means the gas should come out. Only then you will be able to do this, put this upward arrow, right? I think I gave you an example. For example, say I have any metal, right? Reacting for magnesium, any metal reacting with water, right? You will form the like say the hydroxide, and you will see that hydrogen gas will be avoided. So you see, like I'm putting the arrow mark only in the product side if the gas is there, right? Say if at all I have say any gas, like for example CO2 in the product side, I will not write like that. I will write only G. Okay, right? I will not put the upward arrow mark. That represents only evolution of a gas. Okay, next we went on to see this downward arrow mark. Okay, what do you mean with this downward arrow mark, people? What does it represent?
Precipitate.
Yes, right. This tells you that a precipitate is getting formed. I think we saw some reactions. Say if I write Na2, say okay, Na2SO4, no, TDSO4, sorry. So I'll write like this. Let's say if I have NaCl or NaI, we can take. It's better that I take NaI. So if I have NaI, there is sodium iodide reacting with lead sulfate, right? You will form lead iodide plus sodium sulfate. Obviously, you have to balance it and stuff, but you will see that here, this PbI2, I represent with a downward arrow, representing that it is actually going to be an yellow color precipitate, right? Okay, so this we saw, and obviously I can include, third one is I can include whether, like say, the states. That is, I have four choices, either solids, liquids, gases, and aqueous solutions, right? Okay, so I told you when to use what. So solids, or like aqueous solutions you'll use for any salt solution, people. Like say when you have NaI, NaI is a salt. So this is an aqueous solution, I write AQ. This is also AQ. This is not aqueous solution. Na2SO4 is an aqueous solution. Right, so this is another thing, like 1, 2, 3. That is, first is upward arrow, downward arrow, then you can include the states, right? And then last class what we saw is the tests for CO2, H2, and N2, right? This we saw. How will you confirm that CO2 gas is getting evolved, H2 gas is getting evolved, N2 gas is getting evolved, right? Can someone tell me what is the test for CO2? What is the test for CO2? Does anybody remembers? Or if you can look into your notes, if you have taken
Sir,
it.
lime water turning milky, sir.
Absolutely, yes. So it's lime water turning milky. So can someone tell me the reaction of lime water turning milky? What is lime water first?
Calcium hydroxide.
Absolutely, right. Lime water, or it is also called as slaked lime. See, these are all the terms you should remember, people, right? Lime water or slaked lime both represents CaOH twice, right? That is calcium hydroxide. I think you will be able to now guess the formula, how it is CaOH twice. Ca2 plus OH minus, subscribe, you'll get CaOH twice, right? So calcium hydroxide. So then what happens? So calcium hydroxide should react with
Carbon dioxide.
okay, carbon dioxide. It is going to form what?
Calcium.
CaCO3 plus
Calcium
H2O.
carbonate plus
Calcium
water.
carbonate.
Yes, absolutely. Calcium carbonate plus water. So you see, this is the kind of a precipitate which will not dissolve in water. So this is the milky solution, right? So that is what we say, lime water turning milky, right? That is the test you use for carbon dioxide. Okay, good. Next, what is the thing for N2? Sorry, H2. What is the test?
Sir, burning matchstick will burn with an pop sound, sir.
Absolutely right. For H2, all you have to remember is pop sound, right? When I bring burning matchstick in an environment containing H2, it is going to burn with a pop sound. Okay. Now N2, like this is not a good method, but still I can tell that N2 is going to be what to say. It is a it is not going to support combustion. So if there is a burning matchstick, if you bring it in an environment of N2, it is going to put off, right? The flame is put off. Why? Because N2 is a non-supporter of combustion, doesn't support combustion. Okay, so these things we saw, and also we saw this beautiful example where I told you this Mg reacting with O2 to form MgO. There is one thing I wanted you to remember. What is this? What is the phrase which I wanted you to remember? for this reaction, people? Magnesium burns with dash
Dazzling
flame.
white.
Dazzling white
Correct.
flame.
Yes, yes, dazzling white flame. Okay, now before you make this reaction happen, what is the precondition which you have to do? Okay, when I'm going to burn, it's not like I'll have magnesium ribbons with me. Hope you remember we talked in terms of magnesium ribbons, right? So you cannot just take the magnesium ribbon and put it in the flame.
We need to use
That's
sandpaper, sir.
Absolutely. Why do you have to use sandpaper? Why do we have to use sandpaper? Okay, we have to rub the magnesium ribbons with sandpaper. Yes, absolutely, I agree. Why should we do that?
To remove the upper coating.
Correct. So all metals, that to highly reactive metals like magnesium, aluminum, all those things will have a coating, right? And that coating will make it less reactive. It is not going to that much react. So what I do for this purpose, I rub it with the sandpaper so that the upper coating can be removed, and then you do the experiment, and then you put it in the flame, and you are going to form magnesium oxide. Okay, so I think these are all the things which we saw last class, isn't it, people? Right. Okay, so we'll continue today. We'll continue with what are the other stuff. What, like, say now you saw three things. What the extra information which you can give. Other than that, what else we can do? Okay. Now the other things which you can do is, fourth one I'll keep. You can include the reaction conditions, right? So we know that certain reactions will happen at high temperature, certain reactions will happen at low temperature. Say I have some reactions you have to, increase, give a lot of pressure, right? And so certain reactions you have to use something called as a catalyst, right? So now under this reaction conditions, what and all you can include is temperature, pressure, and the last thing is catalyst. Okay, right. Now there is this famous reaction, people. Famous reaction, again, I want you to remember this. There is something called as Haber's process. Okay, Haber's process, or is also called as Haber's reaction. Does somebody know what is Haber's process? Haber's reaction? Okay, no issues. So now in this reaction is basically, this reaction is for formation of ammonia. Ammonia formula, people. Ammonia formula. Ammonia's formula. Let me see how many of you remember.
NH3.
NH3.
Absolutely, yes. It's NH3, right? So we actually require ammonia for so many type of industries. Main thing is agricultural industry. Okay. Now the what is the plants need nitrogen. Like if you're studying your biology, right? Plants need nitrogen for in your root modules, they require nitrogen for nitrogen fixation and stuff, right? So like this ammonia is going to be used for creating fertilizers. Okay, not exactly in the ammonia form, it is going to be the starting material, right? This ammonia will be converted into so many other derivatives, so many other products which can be used in fertilizer industries, in agriculture. Okay, so this ammonia formation is actually a very tricky process. Right. So Haber was a scientist who came up with the reaction. Okay. So what he did is he took nitrogen, N2, and he took hydrogen and he formed ammonia. Okay. Right. Now look at this, people. We have nitrogen in the atmosphere now around us, hydrogen again around us. So why is it that it is not forming? Why is it that ammonia is not getting formed by the reaction of this? Is obviously because the reaction conditions you're talking about, right? Only in those conditions a particular reaction will happen. Okay, right? So only if you provide the necessary conditions, then only we can proceed with the reaction, right? That is the reason why even though we have N2 around us, H2 around us, but this doesn't form naturally. Okay, so what Haber did is he supplied a lot of temperature. He went for around 600. Okay, now, okay, how do we represent it? Right. So now I told you that pressure, temperature, and catalyst can be, included in the chemical equation, and all of these should be included in the arrow mark. Right. We separate the reactants and products with an arrow mark, isn't it? Right. In that arrow mark, you have to include all these reaction conditions. Okay, right. This is how I represent. So this reaction happens at 600 degrees Celsius. Right, and it has to have a pressure of around 300 atm, right? And one more thing is you need some catalyst. Okay, now what are catalysts? I think we already spoke about it. Spoke about this, people. Anybody remembers what is a catalyst?
Sir, we added to make the reaction faster.
Correct. So certain reactions will happen very, 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 very slowly, even though you provide the 600 degrees Celsius, high pressure, high temperature, all these things you supply. Excuse me. Sorry. Yeah. So even though you supply high temperature, high pressure, then also the reaction won't happen efficiently. Okay. So to make it efficient, to make it faster, we go for certain other chemicals, and that is what is called as catalyst. Okay. So I can mention it here. Catalyst speeds up a reaction, right? Catalyst speeds up the reaction. Okay, now please understand, catalyst will speed up the reaction without involving in the reaction. Please, this is a very important point, people. Speeds up the reaction. Maybe I will write it somewhere down. It will speed up the reaction without involving in the reaction. Right? It is not going to involve, it is just going to increase the speed of the reaction. It has no other role to play. It is not going to be a reactant. It is not a product. It is nothing. It is just a catalyst who is going to increase sometimes it even decreases. Maybe we don't go into the details. For now, you have to understand that they're going to speed up the reaction without involving in the reaction. Okay.
Sir, I have a doubt, sir.
Yeah, please go.
Sir, what is difference between aqueous solution and liquid, sir?
Good question. I'll come to that. Let me complete this and I'll come to the question. Okay, good question. Yeah. So now, as I told, the catalyst again should be included here. So you already included temperature, you already included pressure. The catalyst also can be included. The catalyst is ion, Fe. Okay. So in the arrow mark only, you have to write all these stuff. Okay. So I told you the reaction conditions can be pressure, temperature, catalyst, and they are going to be included only at the arrow mark. Okay, now this is an example you can have. Right, now coming to the question which was asked, what is the difference between liquid and aqueous solution? Is a very good question. We'll look into it. Okay, now people say if I give you an example, you'll understand. Now H2O is a liquid, no issues, right? But if I have NaCl dissolved in water, right? If I dissolve NaCl in water, now water is a liquid, absolutely true. But NaCl dissolved, if NaCl is dissolved in water, it is no more a liquid. Okay, so how do I write it? I write it like NaCl is dissolved in water. How do I represent it? I represent it by putting an aqueous, AQ. What do you mean by aqueous? Aqueous means aqua means water, right? So any salt dissolved in water, right? That particular combination is what is called as aqueous solution. Now, if you have any other pure liquid, no other salt, like nothing is involved in that, only that particular liquid is there, then I put L. Okay, does it answer the question, Kanna?
Yes, sir, I understood.
Okay, right, good, fine. So we saw about reaction conditions and how do you want to include it. And this reaction, you have to remember, people, this reaction you will be encountering, till your 12th class. This N2 plus H2 giving NH3, and please go for balancing it. This reaction N2 plus H2 giving NH3, please balance it, guys. And tell me what is the balanced chemical equation for this.
Sir, and precipitate is insoluble in solid, sir, which is not which cannot dissolve in water, sir. Okay, sir.
Yeah, it will not dissolve. See, in this case, if you look at, where is it? Yeah, if you look at this reaction, PbI2 I have, this PbI2 Again, see, all these are under aqueous conditions. Everything, say NaI dissolved in water, PbSO4 dissolved in water, Na2SO4 dissolved in water. PbI2 will also be in that particular condition only. It will be there in water. But the thing is, why am I not putting it as aqueous solution? It's because it is not getting dissolved. If it dissolves, then I put AQ. If it doesn't dissolve, then I put a precipitate symbol. Yes, understood?
Yes, sir, I got it.
Okay, right. So yeah, balanced chemical equation for this. N2 plus H2 giving ammonia.
So N2 plus 3H2 gives 2NH3, sir.
Absolutely, absolutely. Right. So now you see there is nitrogen and only one nitrogen. So I'll put 2 here. Okay, so a nitrogen gets okay. Now look at hydrogen. I have 2 hydrogens here, and you see there are 2 into 3, 6 hydrogens here. So obviously I have to put 3 here. So N2 plus 3H2 giving 2 ammonia, 600 degrees Celsius, here atmospheric pressure, iron as a catalyst, and this is the reaction. Okay, right, good. So that is about the reaction conditions. Next thing, what you can include in the equation is you can actually determine, if you know some data, right? If you know some data, I will be able to represent whether the equation is endothermic or exothermic. Okay, first things first. What do you mean by exothermic and endothermic, people? Any idea? What do you mean by endothermic reactions, exothermic reactions? What do you mean by them?
So in exothermic, the gas or the heat gets released, and the energy gets released.
Okay. In endothermic?
So it gets taken in.
Absorbed. Okay, I understand. It gets absorbed. So it's very easy, guys. Whenever you see, for example, in this case, right, you have N2 plus H2 giving NH3, you are actually supplying a lot of heat, right? But okay, no, I will not go into detail like that. So, for understand people, now say I write a normal reaction, like a general reaction, A plus B giving C plus D. Okay, right. Now, first thing is, see, reactants are there, right? Now, say, how to put it? Now, these reactants will have some bonds. A will have, say, AA type of bond. B will have BB type of, okay, when I say bond, I'm talking about the attractive force. Okay, I'm talking about the attractive force. Okay, or I will, okay, fine, we'll talk in this way only, no issues, right? So when I say a bond in chemistry, people, right? When I say a chemical bond, a bond is nothing but an attractive force which exists between the particles, right? So remember this, when I say bond in chemistry, it means the attractive force, right? It means the attractive force. So what I have to do is, if you look into this, guys, if you want to make this reaction happen, right? If you want to make this reaction happen, you have to actually break the bonds in the reactant side. Is it not? Right? You have to break the bonds in the reactant side, right? And if you go to the product side, you have this CC bond, say DD bond, and so on and so forth. Now these bonds has to be formed. Is it not? Right? So in the reactant side, bond breaking happens. That is, you have to break the attractive force, right? And in the product side, you will see that I'm going to have bonds getting formed. Okay, right. Now, this is common for any of the reaction for that matter. Any reaction you take, you are going to have, you are going to have bond breaking, and or you are going to have bond formations happening simultaneously. Okay, I hope this point is very, very, very clear to all of you, right? Bond breaking and bond formation happen simultaneously during a reaction. Again, in the reactant side, I break the bonds. In the product side, I form the bonds. Okay, now, when you look at the energy considerations, right? When you look at the energy consideration, right, it is pretty logical to understand that for bond breaking, energy should be supplied. Is it not? Right. Say I have a wooden stick with me. If you want to break it, what do we do? You apply some force. you basically supply some energy. The same logic goes here. If you want to break a bond, right, I have to supply some energy. Okay. And the opposite is going to happen if a bond is formed. Okay. A bond formation, energy is released. Okay, it's obviously opposite. It is going to become more stable, right? We spoke about stability and energy. If you can remember the first class, right? We spoke about stability and energy, isn't it? So when a bond is formed, right? When a bond is formed, the atoms involved in the bond formation, right? The atoms involved in the bond formation attain stability, right? And obviously, if the stability is increased, energy has to get decreased, right? And how the energy will decrease? By giving out the energy. As simple as that. Again, I repeat the point, whatever I told you, right? So, okay, I'll tell you like this. Whenever a bond formation occurs, stability is increased, right? Whenever a bond formation occurs, the atoms involving in the bond formation, they get stabilized, right? So if they get stabilized, energy has to decrease, right? How the energy will decrease? Energy is going to get released from the whatever the process. Okay, so what you understand is there are two different energy processes happening. One is energy being supplied in the reactant side, right? Because I have to break the bonds. And you see in the product side, you see that because of the new bond getting formed, energy is getting released. Okay, right. So now you have to actually, understand, say I have to quantify this. Say this is some X value. The value is X joules. The unit of energy is joules. Okay, now say this is Y joules. Okay, the energy released here is Y joules. Okay, right. Now what you have to understand is, people, for a particular reaction, whether the reaction is endothermic or exothermic depends on both the energy supplied as well as the energy released. Okay, again I repeat, to classify whether a reaction is going to be endothermic or exothermic, you have to include both the bond breaking processes as well as the bond formation process. Or in other words, you have to take in account the energy supplied as well as the energy released. Okay, so if I ask you, what is the overall energy? What is the overall energy change? I write delta E. Delta E is energy change, right? When I put delta, I talk about the difference. This delta, right? I put a triangle symbol. This talks about difference. Okay, so when I put delta E, I'm talking about what is the overall energy change happening, right? So can I say, in this case, I've given you the values here, X and Y, right? So this delta E, I can write it as X minus Y. Is it not? Right? X minus Y, I'll be able to write it like this. This is the overall energy change. Okay, now depending on what is the value of delta E, right? Or I would say, depending on what is the, instead of telling you what is the value, depending on how is the value. Okay, that will be confusing. I'll tell you that point. Don't worry. Right? Depending on how is the value, right? Then I can tell whether the reaction is endothermic or exothermic. Right. So guys, I want you to understand one more thing. Right. There are certain sign conventions we follow. Okay. There are some sign conventions we follow. Right. What are the sign convention? Please remember, whenever energy is absorbed or energy is supplied, that value I give a positive value. Say I tell you that 20 joules of energy is absorbed. Right. If I tell you that 20 joules of energy is getting absorbed, I write plus 20 joules. I give a positive value. Right. If I tell you that, and one more thing is, energy is getting released, right? That should be a negative value. Right? Say I tell you during a reaction, right, some 40 joules of energy is getting released. Right? Now, how should you write it? You should write it as minus 40 joules. Okay, right? Energy supplied should be positive value. Energy released should be a negative value. Okay, so anyways, like this is just an extra information for you. Now, what I'm trying to tell you is you have to look into this, the difference in energy supplied and energy released, right? And if you find that the delta E is greater than 0, What do you mean by this? The delta E greater than 0? This means the energy supplied is greater than energy released. Can I tell these people? This makes sense, right? Delta E greater than 0 means the amount of energy supplied is greater than the energy released. Obviously, right? Say if X is greater than Y, obviously then your delta E will be a positive value. Say it's like 4 minus 3. Say 4 joules of energy is absorbed, 3 joules of energy released. So delta E will be 1 joule. So obviously it is greater than 0. Right? That means what? Delta E is greater than 0 means energy supplied is greater than the energy released. And whenever you see this delta E is greater than 0, that corresponds to an endothermic reaction. Why? Because now delta E is positive, right? It is greater than 0. And I told you here, see, whenever energy is supplied positive, now that should be a positive value. So whenever you see a positive value for energy, that is overall energy, delta E, right? Now that will be an endothermic chemical reaction. Okay, now obviously the exactly opposite will happen if I tell delta E is less than 0, that is if it is negative, right? That means energy released will be greater than energy supply, right? And obviously this will happen if Y value here, right? The Y value which is here, right, is going to be greater. That means what? The energy released during the bond formation processes is greater than the energy supplied during the bond breaking processes, right? Yeah, please go on.
So what does delta mean, sir?
Oh, what is delta E? Delta E, so I'm telling you, there is one side energy getting supplied, another side getting energy getting released. Correct? There are two energies, right? So the difference in energy is what is my delta, X minus Y.
Okay.
Okay, right. So when delta E is greater than 0, positive, endothermic. When delta E is less than 0, that is energy released greater than energy supplied. Now this corresponds to an exothermic chemical reaction, right? So as someone said, endothermic chemical reactions will absorb heat, right? And okay, heat is also a form of energy. I'm talking only in terms of energy here, but you can basically energy is nothing but heat. Okay, so endothermic chemical reaction will absorb heat, right? And exothermic chemical reactions will evolve heat, right? But that doesn't mean that there is no, like say for example, in the endothermic chemical reaction, there is only one process that I am going to have absorption energy. No, it is not like that, right? I told you any chemical reaction for that matter, will have both the things happening. Energy will be supplied, energy will be released. It is all about which energy is greater, right? If the overall, like say, if the energy supplied is greater, then it is endothermic. If the energy released is greater, then it is exothermic. Okay, now how do you represent this particular data, right? If I know, okay, first we understand how it is endothermic, how it is exothermic, and how are we going to incorporate it in the equation is the next question. Right now, guys, for example, if I just take an endothermic random reaction, right? Okay, I have an endothermic reaction with me, right? Say I have A giving B is an endothermic reaction. Okay, right. Now, if you want to specify that this is a endothermic chemical reaction, obviously you understand that energy has to get supplied. Energy is to be supplied. Right. So what you have to do is along with the reactant, obviously you are going to supply the energy along with the reactant. Correct. Say assume that some 50 joules of energy is getting supplied. Okay. So you should write A plus 50 joules will give B. Okay. This is how you write an endothermic chemical reaction, but you have to know the value. If you don't know the value, don't include it. Okay. So this is another data which you can include. Right, the energy consideration. You can, if it is endothermic chemical reaction, put the energy value in the reactant side, obviously because energy is getting supplied. Correct. Now, if I have an exothermic chemical reaction where energy is getting released, say A giving B is a reaction. Right. Now, energy is getting released, and I say that say 50 joules of energy is getting released. Right. Obviously, the energy is coming out along with the products. Right. Energy is coming out along with the products. So in the product side, you write 50 joules. This is one way of writing it. Okay, this is one way of writing it, just putting the energy along with the reactants and products. Endothermic means in the reactant side, exothermic means in the product side. Okay, now if you do not want to do this, right, if you don't want to include the energy considerations like this, now there is this term called as, now we know delta E, right? Delta E is difference in energy. Now instead of E, I'm going to write H, delta H. Now we don't have to go into the details, people. All you have to understand, delta E is nothing but it's called enthalpy, right? Again, you don't have to worry about what is enthalpy. Enthalpy is energy. That's all you have to understand. Okay, right? I'm introducing to a new term called delta H. Right, delta H, what is it called as? Delta H is called as enthalpy. Right, enthalpy is nothing but energy. Okay, now you will study about it more when you come to 11th class in a chapter called as thermodynamics. Right, you will be studying about what is delta H. We don't have to go into the details now. Okay, now I told you that overall energy should be, so you can look at here, right? Where is this delta? Yeah, look at this. Delta E greater than 0 is endothermic. I can even write delta H greater than 0, then it is going to be endothermic. And same way, here I wrote delta E less than 0, that is overall negative, is exothermic. I can even write delta H less than 0. Okay, now if it is an endothermic process like this, how will I represent with the help of delta H? I represent it like this: A giving B. I don't include any numbers here in the reactant side, right? But in the side of the reaction, I write like this: delta H. What is the value? I know the delta H, the energy value is 50, right? But you have to be very, 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 very careful with the sign, right? For endothermic processes, I told you delta H is positive, right? For endothermic processes, delta H is positive. So you write delta H is equal to plus 50 joules. Okay, now for this reaction, again I write A giving B is the overall reaction. I don't include any numbers in the reaction, in the reactants or products, but in the side, I write delta H or delta, we don't write delta E, we write delta H as 50, but again, the sign is very important. You see it's an exothermic chemical reaction. So you write minus 50 joules. Okay, right? So this is how we represent people, right? There are two ways of representing whether a chemical reaction is endothermic or exothermic. One is including the numbers along with the product side, or in the reactant side or product side, or you include with the help of this delta H. Okay, now delta H will be positive for endothermic processes, and delta H will be negative for exothermic processes, and that is exactly how we write. Okay, now I hope everybody understood. I have to get a yes from all of you people. Did you guys understand? Everybody put in the chat box or you unmute yourself and speak. Is there any doubt? Everything is clear or not? Everything is clear?
Yes.
Understood.
Yes, sir.
Okay. So I hope everything is clear. Maybe we are looking into a lot of new stuff today, right? But don't worry about it, right? This is all purely logical. There is nothing you have to, mug up, nothing like that. Okay, we just spoke about how it is endothermic, how it is exothermic, and how are we going to represent it, right? How are we going to represent it in the chemical equation? That's all we saw. Okay, right, cool. We continue. So now we locked up. So we saw it started with upward arrow, downward arrow, solid, liquid, gas, and then we went on to see this exothermic. No, before that we saw reaction conditions, temperature, pressure, catalyst. How do we include it in the arrow mark? You have to include. And lastly, we saw how to represent an endothermic or exothermic chemical reaction. Right. So guys, the questions can be like this. They will give you a reaction, right? And they'll give you delta H value like this, right? Delta H is plus 50 or minus 50, whatever it is, they'll give you the value. And they will ask you whether the reaction is endothermic or exothermic, right? And what you have to do, you just have to look into the sign. If the delta H value is positive, then I give it's a endothermic reaction. If you find the value is negative, then it is an exothermic reaction. Like this kind of questions can be asked. Okay, right. So that is about the other. These are, I think, that is it. Okay, now these are all the different types of extra information you will be able to give with respect to a chemical equation. Okay, right, fine. Now we'll move on. we'll move on to, or maybe I'll give you, okay, fine. Maybe we'll move on to the types of chemical reactions. Yeah, we are going to the last part of the chapter, people. Okay, fine. So this is the last part of the chapter talking about what are the different types of chemical reactions you have. Okay, now under this, the first one are what are called as combination reactions, right? Combination reaction. Okay, now what do you, like, how do I represent it? From the name itself, you can understand two things combined together to form another product, right? Say I write it like this, A plus B giving C, right? So you see two things, merging together to form one single product. Now, please understand, people, I should have only one single product in case of a combination reaction. I should not have multiple products. There should be only one product, right? Say if at all you want example, we can take the example of magnesium plus oxygen. Magnesium plus oxygen giving MgO is the reaction. And you see, you have A, you have B forming C. Very simple. Okay, right? Fine. Now, next. First, that is an example for combination. Like, see, guys, the questions will come like this. They will give you some reactions and they'll ask you to find what is the type of the chemical reaction, right? So now one of them you know now is, what is that? Combination reaction. Next one is decomposition reaction, right? Now it is exactly opposite of combination, right? Here I should have only one reactant. Very important, right? Now we know it's decomposing means what? One thing is getting separated into multiple stuff. A big piece, right? A big chunk is getting separated into smaller stuff, right? So in combination reaction, there should be only one product, right? In decomposition reaction, there should be only one reactant. Okay, there should be only one reactant. Okay, now if at all I want to give you an example, right? So this calcium carbonate is there. Okay, now if you calcium carbonate, okay. Now one more thing I forgot to tell you in this, where is this reaction conditions, guys? You will be able to include one more thing, right? You can also include what to say, whether you're heating it or not. Right? Now, how do you represent it? That I'll tell you now. I will represent it like this. Okay. Now I'll represent it by putting a triangle symbol. This is very important, people. Okay. So whenever there's an arrow mark and above the arrow mark, I have a triangle symbol like this. That means I am heating this particular mixture or I'm heating this particular compound. Please remember this. Okay. Delta symbol. I mean, this is not delta symbol. This is okay. We can call it as delta. Whatever it is, this symbol, right, represents that I am heating the mixture. That is how I represent it, delta. Now that delta E, whatever we saw, that talks about the difference. Okay. Now this delta talks about what? This delta talks about heating. Okay. So when I'm going to heat CaCO3, I am actually going to get calcium oxide and carbon dioxide gas will be evolved. Okay. Yeah, carbon dioxide gas will become evolved. So again, see, I put an upward arrow like this. Okay. Now this CaO will be solid state. CaCO3 will be in solid state. Okay. Now you see there is only one reactant becoming two products. Again, it is decomposing. Okay. Right. That is about decomposition reaction. Right. Okay. Now moving on. Third one is displacement reaction. Right? So what do you mean by displacement reaction, people? I'll write a general equation first. Okay. Now general equation, I can write AB plus C gives, say, AC plus B. Okay. Now what I'm trying to do here is, you see, initially A and B were together, right? So C comes, C is going to replace this B. in the reactant. So you see, I'm forming AC and B is coming out. Okay, so one of the things, it is getting displaced from its compound. Okay, now if at all I have to give you a reaction, I have to give you an example. There are so many examples, right? Say for example, if I have say NgCl2 and I react with sodium, I am going to get NaCl and Mg is going to get released, right? Mg is coming out, that is magnesium metal is going to come out. Okay, now you see chlorine, chloride ion, right? Chloride ion was with magnesium, but in the product side, the sodium ion has the chloride ion and magnesium is going to come out as metal. Okay, now can I have the opposite happening? Say for example, if I have NaCl and if I react with magnesium, can I form NgCl2 plus Na? That is basically the opposite of this reaction, right? Now, how do we understand which is correct? Right? How do we understand? Because this is also a displacement reaction. This is also a displacement reaction. But how will we know which is correct and which is wrong? For that, people, you have to understand there is something called as reactivity series. Right? There is something called as reactivity series. Okay, this reactivity series is nothing but I am going to arrange the elements, I'm going to arrange the metals in the order of the reactivity. Okay, now for now you have to, there is no other choice than to mug it up, right? But when you go to periodic table, we'll study about, as I told you, one of the chapters you have is periodic table. Once you understand the periodic table, there is no mugging up. Okay, but for now, till we reach the periodic table chapter, whatever the thing which I'm going to give you, you have to remember this. Okay, right. So this thing goes like this. Potassium K is going to have, one second guys, one second, there's a lot of background noise. Just give me a minute. Okay, fine, we continue. Right, now it's a little better. Right, so what I was telling is, I was talking about this reactivity series, right? Potassium is the most reactive element. Then comes sodium, then comes calcium, magnesium, sodium, potassium, okay. Then I can have lithium, then comes aluminium, then I can have iron, then comes hydrogen, then comes copper, gold, silver. Okay. Right? This is Ag. Ag is silver. Okay, this is G. Okay, Ag is silver, Au is gold. Okay, now this you have to remember, people. Okay, now I'm telling you, you have to remember only for now. Right? Once we move on to the periodic table chapter, you will understand what is the logic behind this. Okay, why is it coming like this? Okay, so you see here, now for the reaction which we wrote, for the first reaction and second, and we will check whether it's correct or not. Now, please understand one thing, one phrase I want you to remember. All right, the phrase is, for a displacement reaction, more reactive element or more reactive metal displaces less reactive 1. Right? So whichever element is more reactive, that element is capable of replacing the other element from its salt. Right? So if I can go to this first, whatever it is, like you see here, right? So what is happening? B is getting replaced by C, right? B is getting replaced by C. So what I can tell about this is that C is more reactive than B. That's what I understand. I told you, more reactive metal displaces the lesser reactive one. Right now, in this case, you see B is getting displaced by C in the product side. So what I can tell is the C is more reactive than B. Okay. Now, from the reactivity series, look at this. Right. So see, now there are two metals involved. One is sodium, the other one is magnesium. Right. One is sodium, the other one is magnesium. So look at where sodium is. Sodium is here. Magnesium is here. Right. So what I understand from here, sodium is more reactive than magnesium. From the reactivity series, I'm telling. Right. Sodium is more reactive than magnesium. That means what? Can I say this reaction is completely all right? Why? Because sodium is more reactive and magnesium is less reactive, and sodium is replacing magnesium or displacing magnesium in the product set. Right? But if you look at the second reaction which we wrote, right, what is happening? This reaction, what I'm writing is magnesium is, we know it's less reactive and sodium is more reactive. But what is happening? Magnesium is replacing sodium. So this reaction is absolutely not possible. Okay. So the displacement reaction will happen only if a more reactive metal displaces a less reactive metal. The opposite is not possible. Okay. That's why we say second reaction is not possible. Now say if I ask you a question. Right. So I write another reaction. You have copper reacting with HCl to form copper chloride plus hydrogen gas is getting evolved. Okay. Now look at the reactivity series. Maybe I'll look at the reactivity series and tell me whether this reaction is possible or not. Hope you're able to see the reactivity series. You see where is copper, where is hydrogen, and tell me whether this reaction is possible or not.
Sir, it is not possible.
Absolutely, it is not possible. Now, why? Because you see, hydrogen is here, right? And copper is after hydrogen. That means what? Hydrogen is more reactive than copper. From the reactivity series, I'll be able to tell. So what do you think is happening here? Here, copper and hydrogen is there. Copper is less reactive. Hydrogen is more reactive. But what you see is happening is that copper is replacing hydrogen, right? And that is not possible. Why? Because hydrogen is more reactive than copper. So this reaction is not possible. Okay, right? So why this reaction? So that means copper basically will not react with any acids, right? Copper, iron, sorry, not iron, copper, what is that? Gold, silver, all these are inert. There's this thing you can know actually, inert, right? Inert means not reactive. Right. So I'm saying copper is inert, or copper, gold, and silver are inert to acids. And that is the reason why we use them in your so many applications, right? In your wires and so on and so forth. Because if you have any acid present, they will not corrode. Right? Acid have a property of corroding substances, isn't it? Right. So that is the reason why we go for copper, gold, and silver in your so many kinds of purposes. Okay. Right. Fine. So that is about the displacement reaction. All you have to understand is more reactive metal displaces less reactive one. And second thing you have to remember is the reactivity series. Okay, right? Fine. So that is about displacement reactions. We'll move on to the fourth type. It is called double displacement. Double displacement reactions. Okay, what is the time? Okay, we have 5 more minutes. Okay, now this is again a displacement reaction, but the difference here is you see here only metal gets displaced, right? Or I would say only cation displaces. But in case of a double displacement reaction, both cation and anion gets displaced. Right. Now, the famous equation we have, that is, say I had NaI reacting with PbSO4, forming Na2SO4 plus PbI2. Now you see everything is changing. Initially sodium was with iodine, right? And lead was with sulfate, right? But see what is happening here. Now sodium is with sulfate and lead is with iodine. Okay, that is what I'm telling. Both cation and anion gets displaced, right? So if both cation and anion gets displaced, that is an example for the double displacement reaction. So if at all you want a general equation, I can write like this: AB plus CD gives, say, AC plus BD, something like that, right? This is B, if I can write it properly. Okay, right? So this is what is called as your double displacement reaction. Right. Okay. And at last, we have one more this thing, that is what is called as combustion reaction. And I think we already spoke about it. Can someone define what is combustion, people? Can someone define combustion reaction?
Substance burns in the presence of oxygen.
Absolutely. That's it. That burning with oxygen. Right, burning with O2 is what is your combustion reaction, right? So you can have so many reactions happening. Say I can have Mg plus O2 giving MgO is a combustion reaction. Say I have methane burning in oxygen to form CO2 and H2O. All these stuff, all these are combustion reaction. So the moment you see oxygen in the reactant side, right? The moment you see oxygen in the reactant side, all of them will be combustion reaction. I can even write it here. Maybe I write at the top. Oxygen, O2 in reactant side. If you see, then that moment itself, you can understand that it is going to be a combustion reaction, burning with oxygen. Okay. Now, so this particular thing you see, Mg plus O2 giving MgO can be both a combination reaction as well as a combustion reaction, right? So in the exam, if it comes and they give you this Mg plus O2 giving MgO, ask you to write what type of reaction it is, you can write either combination or you can write combustion. Both are correct. Okay, because we remember, like we saw the example here also for combination, right? Mg plus O2 giving MgO, right? So that is, you can write either combination reaction or you can write combustion reaction. Both of them are absolutely correct. Okay, right? Other than this, right, I have, what is the time? Maybe I'll continue next class. Okay, so we have oxidation reduction, and then we'll see something about corrosion, transitivity and stuff, and we are done. Okay, I just need maybe 15 to 20 more minutes next class, and we'll be going for the second chapter. Second chapter is acid, bases, and salts. Now I'm going to give you a homework. The homework is solve all the book back. Right, at the end of the chapter, you will have so many questions. Right, you will have so many questions at the end of the chapter. I want you to solve all the possible questions, and that has to be submitted next week. Okay, and that has to be submitted next week, and you have to personally WhatsApp me. Right, you write it, right, and you take a picture, or there are a lot of apps, Adobe Scan, Cam Scanner and stuff. Okay, make it into a PDF, and that has to be submitted before you come to the class next week, next Sunday. Right, if you're not submitting, please don't come to the class. Okay, this is not like, I'm making you do some work. It's all about practicing. Now that you know all the reactions, what and all is there in the chapter, now what is the point if you don't put it into use? Right, that is why I'm telling, solve all the book. How many other questions you have? I think you will have some, maybe 20 to 30 questions, I'm not sure. I want all, like, other than the oxidation reduction, which you're going to see, only a small part is left. Other than that, all the questions has to be submitted next week. WhatsApp me and I'll check, like, tell your name. Obviously, I'll not have your numbers. When you send it in the WhatsApp, tell me your name and then send it. Okay, is that cool? Will you all do it?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, this is only for your benefit. I am not going to gain anything. Okay, if you try it out, it is going to be very, very, very easy for you for your board exams. Okay, so solve all these stuff. Okay, all the book back exercises before you come to the next week class, submit it. Yes, any questions?
Sir,
So
next
next we
week you teach 11 activities, sir. Actually, in book 11 activities are given, sir.
Oh, okay. I will look into that also. Sure.
Okay,
Maybe I'll teach you all the 11 activities also, and oxidation reduction also. All those I'll teach you. But before that, this has to be submitted.
Okay.
Okay. Right. Cool.
Yes, sir.
Okay, guys. If there are no questions, I think we can wind up the class.
Thank you, sir.
Okay. Thank you so much.
Thank you, sir.
Yes, sir.
Thank you, sir. Thank you, sir.
Thank you. Thank you.